Here on planet Earth, objects accelerate due to gravity at the same rate. Here's an example. I'll take these two pens and I'll drop them and they hit the table at the same time. That's no surprise. We might expect that because these pens are the same weight. But what if I took two pens and joined them together to make a single object? Now this object is obviously twice as heavy as this one, but when I drop them to the table, they still hit the table at the same time. The acceleration due to gravity here on planet Earth acts or gives the same acceleration to all objects regardless of their mass. Here's another one. I've got a piece of paper that I've wadded up into a ball and a koosh ball that is much heavier than the piece of paper, and when I drop them, they hit the table at the same time. We call this free fall acceleration. And what that means when we say the word free fall, it means we neglect the effects of the air. If we don't neglect the effects of the air, then we can see there's quite a big difference. Here's a single piece of paper that's not crumpled into a ball, and the same size piece of paper that is crumpled into a ball, and when I drop them, obviously this one hits the table first. It accelerates faster because this one is very susceptible to the effects of air resistance, of the wind acting on the piece of paper. Why didn't we see as obvious an effect on these two objects? Well, that's because at slow speeds, those objects aren't really moving very fast yet. At slow speeds, the effects of the wind are negligible. They're barely noticeable. So when we're talking about free fall acceleration, that's what we're going to be talking about. The times when the air resistance or the effects of the wind are negligible.
Atmospheric pressure.
3, 2, 1.
Vacuum.
3, 2, 1.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Here's our ticker timer device, which we know records displacement as a function of time. I'll attach a heavy weight to my ticker tape with a piece of masking tape, and then I'll let the weight fall and pull the tape through the machine, making marks on the paper every 60th of a second. So here we see the ticker tape produced from this experiment. The cluster of dots near the 0 is where the machine was turned on, yet the tape had not begun to move through the machine yet. In other words, I had not dropped the weight yet. Then, after I drop the weight, the tape is pulled through the machine, and you can see that as time goes on, each dot is separated by 1/60th of a second in time, but you can tell that the distance between the dots begins to increase. This is indicative of the acceleration that is occurring as the weight falls. For each time interval, the distance traveled is greater and greater. I'm going to set up my LabQuest device with my motion detector, which will make a plot of position as a function of time and velocity as a function of time for objects that are moving in front of the sensor. So I'm just going to set it down on the table, and I'm going to take this can of soda, and I'm going to record the data as I throw the can of soda into the air, and it will record the motion as the can flies up and down. Here we go. Start. Let's take a look at the graphs. So here are the graphs generated. We have position as a function of time, and we have velocity as a function of time. Looking at the position graph first, we see that it starts at, looks like about 32 centimeters above the sensor, and it flies up into the air to a maximum height of about 44 centimeters, and then back down to where it started from. And this happens in a time interval from 6.9 seconds to 7.2 seconds from the time I pushed the start button on the LabQuest. In the velocity graph, if we look at this section of free fall, that is the time the can was only in the air, not under the influence of my hand at all, but only under the influence of gravity, that time of free fall, I can look at the velocity time graph, and I can, first of all, I see that it's a straight line, indicating that I have constant acceleration. And the slope, or the rate of change of my velocity, we see here is negative 9.8, which matches very well with the value we expect for the acceleration of gravity here on Earth. It started at some positive velocity as it moved upward, and then as it neared the top, we can see the velocity decreased, got closer to zero, until at the very top of the parabola, the velocity is 0 meters per second. And then it starts to come back down, so now my velocity is in the negative region, and it is moving downward. That's what the negative sign indicates for a negative velocity, but the slope is still the same. So that tells me on the way up, at the very top, and on the way down, the slope is the same in all those places. So the acceleration is always negative 9.8, regardless of whether it's going up at the top and instantaneously at rest. Only a brief moment is the velocity 0, and on the way down. The whole time, the acceleration is negative 9.8 meters per second squared. Let's talk about the sign of acceleration, plus or minus. It's conventional to say up is the positive direction, so of course then down would be the negative direction. Gravity always acts down, of course, so that's why we often say gravity is negative 9.8 meters per second squared, because it's in the negative direction. Let's look at an example of just throwing an object up into the air. On the way up, the velocity is upwards, so it is positive. But gravity is always down. So the acceleration due to gravity is negative. And while the object is rising in the air, it's slowing down. It reaches the top, and then it starts to come back down. So now on the way down, the velocity is in the negative direction, and the acceleration is still in the negative direction. The whole time the object's in the air, the acceleration is down. And as something falls from a higher height, we know it speeds up. Okay, so here we see that when velocity and acceleration have opposite signs, the object is slowing down. And when velocity and acceleration have the same sign, the object is speeding up. All right, so Advaith here, we're going to test his reaction time. I'm going to drop the ruler. It will start at the 0 centimeter mark, and I won't let him know when I'm going to drop it. It'll fall. He'll close his fingers as fast as he can, and we're going to record in this table the distance the ruler falls, and then using our equations of motion, we'll be able to calculate his reaction time. So here we go. Put your hand even with that. Yeah, right there. Okay. So he does not know when I'm going to drop it. All right. So the first one, 22 centimeters. So we're going to record that in our table here. 0.22 meters. Here we go, we'll do it again. Oh, we got a little better that time. 18. All right, and one more. 18 and a half. There we go. So I've recorded our data. We're going to take the average, and we're going to use our equations of motion to figure out what his reaction time is. Thank you, Advaith. Awesome. All right, so let's take our average, 0.22 plus 0.18 plus 0.185, and divide that by 3, and we see our average is 0.195 meters. So to calculate our reaction time, we're going to use our equation of motion that says displacement is equal to initial velocity times time plus 1/2 at squared. We know that the ruler starts from rest, so the initial velocity is 0. So this term drops out of the equation, and I know that the acceleration due to gravity is 9.8 meters per second squared, and the displacement, we're going to use this number here. Our average is 0.195. So let's solve that for t. So 0.195 times 2 divided by 9.8, and take the square root of that number to come up with 0.19948, or 0.2 seconds. 0.20 seconds reaction time.